Hello everyone, this is Doug, and I just want to take a couple minutes to introduce the idea of buffer solutions to you. We're not going to do anything real quantitative, just kind of what they are in general, how to spot them, and why they matter. So buffers, right, are just a solution that resists a change in pH. So the most of the solutions that we're going to be talking about are aqueous. So by the solutions, I'll put here aqueous. They don't have to be aqueous, but again, we're talking about biological systems a lot, or just normal things that you see out in the everyday world. Water is usually the solvent, so usually aqueous. And they resist a change in pH, right, which is really a measurement of the concentration of H+. But of course, if you're in water, then you might also see in books and out in the world hydronium instead. H plus or hydronium, either way, same thing, right? The idea of the acid, the H that's released by some sort of acid. And you find these buffer solutions in all kinds of different things, right? We got some important ones in things like blood and intracellular fluids. We got orange juice, things like beer. There's just buffered solutions all over the place. And a buffered solution is established by an equilibrium, and I want to emphasize that. Super important that it's an equilibrium. And it's between a weak acid and its conjugate base. So weak acid, conjugate base. And the idea of how buffers work is just Le Chatelier's principle. So we already talked about Le Chatelier's principle, and I'll show you it again here in a second. But if I looked at these pairs and asked myself, are any of these buffers, right? So I've got HCl and NaCl, right? I should look at HCl and be like, oh, wait, I know that that's a strong acid. So since that's a strong acid, that means that this cannot be a buffer, right? And the idea here is that if it's a strong acids are defined as basically dissociating 100%. So that means that I do not have an equilibrium here, right? This is a one-way arrow. This is 100%. This is not an equilibrium, so no equilibrium. Which is why it cannot be involved in a buffered solution. It's not going to work. Similarly, if I go to the second one, right, so I've got sodium hydroxide and water. Sodium hydroxide is a strong base, and water is its conjugate, so that's also not going to be a buffered solution for similar reasons, right? If I look at NaOH in water, right, you're just going to end up getting the same things back. Sorry, not an equilibrium. It just completely dissociates also to give you Na plus and OH minus, and that's a one-way reaction also. But if I take a look at something like acetic acid and acetate, so I've got acetic acid and acetate. Now I do have something that is in equilibrium, right? So I've got the HC2H3O2, so acetic acid, that is in equilibrium with the H plus C2H3O minus 2. Right, because that is a weak acid, right? Acetic acid is a weak acid, which means that it does not dissociate 100%, that there is an equilibrium here. And since we have an equilibrium, that means we can do Le Chatelier's principle can take over, right? So once we're at equilibrium and there's something that disrupts that equilibrium, that perturbs that equilibrium, it will shift left or shift right in order to fix that perturbation, right? So that's how we're going to see that the pH ends up staying the same, or that something resists a change in pH here in a sec. So this would be a buffer solution, right? So this would be a buffer. This can make a buffer. And I won't go through all the steps for this one down here, but again, if you recognize that HF is also a weak acid, then you should be able to make a buffer between HF and F minus also, right? HF is a weak acid, it's not a strong acid, so there is an equilibrium for HF and F minus also. So that could also make a buffer solution. And so the idea is anything, whether it's citric acid or phosphoric acid or any sort of weak acid, you can make a buffer solution with. So like, what do we mean by change resists a change in pH? Let me show you a couple of examples. All right, so say I have these three solutions, right? So I have solution 1, 2, and 3 here. So or let me just call this solution A, this solution B, and solution C. In A, I just have a solution of water, so this would just be pure water, 100 milliliters of pure water, in which, so our pH is 7 here, right? So nice and neutral, super pure, deionized water, distilled water. And the idea here is that I'm going to add 10 milliliters of a 1 molar solution of HCl, right? So HCl is an acid, so I'm expecting the pH to drop, right? So this should lower my pH, right? Because we're adding acid. It's going to become more acidic, so lower pH. And if you do that, I don't care about the math. I don't need you guys to do the math, but it's just conceptually, right? If I add 1 molar solution, 10 milliliters of a 1 molar solution, that's actually going to drop my pH all the way down here to 1.04. It's going to drop like crazy. There's a big, big drop, right? That's the idea. There's a very large drop in pH. So I'm going to write that here. Large drop in pH. Which, if this was your blood, that would be a huge, huge problem because your blood needs to be at 7.4, not wiggling around too much. If your blood pH dropped all the way to 1, you would be so dead. If I take a look at solution B here, 100 milliliters of a 1 molar solution of NaCl, right? NaCl, this is not what we talked about as far as forming buffers, right? NaCl is just salt, just table salt. It's not a weak acid and it's conjugate base. It's only one thing. Its pH is also 7, right? Because sodium chloride is neither acidic nor basic. Same thing, if I add that same 10 milliliters of a 1 molar acetic acid, I expect the same thing. I expect to see my pH drop. Which in fact we do, right? If you take a look at this, you see the exact same change. You see a very, very large change in pH, so a large drop in pH. Oops. So large drop in pH. So we would say that neither of these have like no buffering capability whatsoever. That's the idea, is they have like no buffering capability. They did not resist that pH change at all. So no buffering capability. However, if you take a solution of that acetic acid and acetate that we talked about before, and you do the same thing, right? So here I have a solution of 1 molar acetic acid and 1 molar acetate, sodium acetate. The pH is going to start off lower at 4.74, and you can make different buffer solutions at whatever pH you want, basically. You just have to kind of tweak the ratios, maybe use a different acid and base. But you just got to tweak the ratios. In this particular example, we're at a pH of 7.4, so we're already pretty acidic. And now I'm going to add that same amount, right, 10 milliliters of a 1 molar hydrochloric acid. And so again, I expect a pH drop. Now, these ones up here both dropped a pH of 6, or they dropped by 6 pH units, so 10 to the 6th change in concentration. If you look at this one, though, what we see here is that it did not drop that much. It went from 7.4 to, or sorry, 4.74 to 4.65. It didn't drop that much. It was a much smaller change, right? This was a much smaller change in pH. So I'll put a small change in pH. It didn't change that much, even though I added a bunch of a very strong acid. So this is what we mean by when things resist a change in pH, that they don't change pHs that much. It's not that big of a difference is the idea. So this would have some buffering capability. This would be an example of a buffer. Right, so this would be a buffered solution because it didn't change its pH that much. It resisted that change is the idea. So how exactly is it doing this? How is this working? Right, remember that when we're talking about resisting a change in the pH and we have these buffer systems, the whole idea is that we're at equilibrium, right? So you got to keep that in mind, is that we're at equilibrium. So that's why these are, again, weak acids and weak bases. So equilibrium. Which means once you're at equilibrium, it wants to stay at those equilibrium ratios, right? So, and Le Chatelier's principle, right, remember, just that says that when a reaction is already at equilibrium, if you disturb it, if you perturb it, it's just going to react in a way that reestablishes that equilibrium. So let's say you have some sort of event here where something happens where the pH increases. The pH increases, in other words, the concentration of your H plus goes down, right? So whether it's someone's hyperventilating, maybe there's a bunch of amines being released, maybe all kinds of things. The idea is that your concentration of H plus is going to decrease, right? And so we can just go right back to that good old Le Chatelier's principle stuff and ask ourselves, well, what happens if you have a decrease in that product? What happens if that goes down? And so the response, right, again, this is just Le Chatelier's principle as far as are we going to shift left or shift right. Anytime you take away a product, right, the problem is that now there's not enough of that product. And so what happens is that you shift right and shifting right. So shift right. Right, again, this is just old Le Chatelier principle type stuff. If you shift right, that means that the forward reaction is occurring. So that means you have a decrease in this and an increase in that and an increase in that. And so you'll notice that the amount of carbonic acid decreases here, the amount of my bicarbonate increases, but the amount of my H plus increases, right? So what we're going to see is that the concentration of H plus increases as a result also. So you can see that I have kind of two things going on here, right? First, the amount of H plus decreased because something happened where it was being consumed, but because we have a buffer solution, because it's an equilibrium, and because we have Le Chatelier's principle, when you shift right, you end up just making more of that H plus. So you sort of fix it, right? So you take away and add, right? So H plus was removed, but then also added. So removed and added, and so therefore there's a small change, only a small change in the amounts of H plus and the concentration of H plus. So we've resisted a change in pH. We've resisted a big change in that H plus concentration. We can see the same thing down here, right? So if we had some sort of event, right, something that perturbed it, something that messed up this equilibrium, right? So let's say you're doing glycolysis, right? You're making lactic acid or something like that. The idea, if you're making lactic acid, is that your concentration of H plus is going to start to increase, which means your pH is dropping, right? So let's say that that's the problem here, is that the problem is that your concentration of H plus is getting too high. And so what's going to be the response from this buffer? What's going to be the response according to Le Chatelier's principle? Well, now if I have too much of the products, I'm going to have to shift right to fix that problem. So now we're going to, shift left. So we're going to shift left, or in other words, we're doing the back reaction. So if you shift left, now that means that I'm going to the left, so I'm going to make more of this H2PO4 minus, but that uses up H plus and that uses up the HPO4 minus too, right, if I'm doing the back reaction. And so again, we see the same thing here, where the H plus, yes, initially, like I put in green, it increased, but the response from Le Chatelier's principle makes it go back down. And so again, there's only a small change in the concentration of H plus. So it's a buffered solution, right? It resists a change in pH, and that's just because you have something within equilibrium. So we just follow Le Chatelier's principle, right? When you take away stuff, add stuff, the equilibrium responds. That's all I really need for you to know about buffered solutions. That's kind of how they work. Now, there is crazy math you can do with them, and you can predict exactly what the pH is going to be before and after and everything like that. I don't really care about that. This is just an introduction to the concept of buffered solutions. If you have any questions or comments, please leave them down below. Happy studying.